Hey guys, we're solving 9701 May June 2022 paper 1-2 today. So starting from this year, the duration has been increased to 1 hour 15 minutes and we no longer have a section B. Alright, so the threshold for this paper was this is paper 1-2, right? So A was at 24, B was at 21, C was at 17, D was at 14, and E was at 11. So if you compare this threshold to variant 1-1, this paper was a bit harder because the threshold was lower, and the maximum mark was 40. So A star should be at around 30. It should be around 30, right? 30 to 32, around that range. Approximately 30. Okay, it's not mentioned in the threshold. So a lot of my students actually gave this exam, and I'm really proud of some of them. The maximum mark was 95. A lot of them got 95. Yeah, so that's that. Let's begin then. Starting with question number 1. Equations involving 4 enthalpy changes are shown, which represents the second ionization energy of sodium. Okay, so W is the first ionization energy, and X is the first plus second IE. Do you understand? This isn't ionization energy. This isn't ionization energy either because the state has to be gas. So I'm excluding these two. So to find out the second ionization energy, what do we need to do? It's gonna be first plus second minus first, right? So it's actually X minus W. All right. So one is C. Moving on to 2. The question refers to isolated gaseous atoms in the ground state, in which atom are all electrons paired. Okay. So yeah, we have access to the periodic table actually. Wait, let me bring that from variant 1-1. Also, guys, I am going to be solving all variants for 2022, so keep an eye on the channel if you're interested. Wait up, yeah, here. Okay, so um, barium. Barium is an S block element. 1, 2, 3, 4, 5, 6. It's 6s2. 6s2. Basically, if you look at barium, um, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, then 4p6, and so on. And if you go to barium at the end, it's going to be 6s2. So in fact, barium has all paired electrons. Barium is the correct answer because it ends at 6s2. What about the others? Why aren't they correct? Bromine. What's wrong with bromine? Bromine ends at 4p5. Remember, halogens do not have all paired electrons. For the halogen, it's like this. 1, 2, 3, 4, 5. It has one unpaired electron. Okay, that's why bromine is out. What about sulfur? Sulfur is in group 16. So for group 16 elements, it's gonna end at 3p4. Okay, so it's like 1, 2, 3, 4. Two unpaired electrons. Do you understand? And what about silicon? Silicon is 1s2, 2s2, 2p6, 3s2, 3p2, 3p2. So it's like this. It has two unpaired electrons. Do you understand? That's why silicon is also excluded. That's that. Moving to 3. Which sample contains the most iodine? Interesting. So what do we have to do? Essentially, we need to find out the moles of the compound. Okay. So for 1, we have calcium and iodide. Calcium is 40.1 and iodine is 126.9. Okay, so for A, it's going to be mass divided by MR, 40.1 plus 126.9 plus 126.9. Okay, so 126.9 into 2 plus 40.1 1 divided by answer. That gives us a value of 3.4 into 10 to the power minus 3 moles. Now, how many iodine atoms do we have? Basically, we can consider it in terms of moles. If you multiply by this by 2, you're going to get the moles of iodine as 6.8 into 10 to the power minus 3. So you have 6.8 into 10 to the power minus 3 moles of iodide for A. Okay, let's go to option B, potassium iodide. Potassium is 39.1. Okay, so for potassium, it's going to be 1 divided by 39.1 plus 126.9. 126.9 plus 39.1. 1 divided by answer is 6.0 into 10 to the power minus 3. So this is 6.0 into 10 to the power minus 3. I'm not multiplying it by 2 because it's just I, 1I. Now for sodium. Okay, so this is going to be 1 divided by sodium has 23. 23 plus 126.9. So 23 plus 126.9. 1 divided by answer gives us a value of 6.67. 6.67 into 10 to the power minus 3. Interesting. This is 6.67 into 10 to the power minus 3. Last one, ammonium iodide. So nitrogen is 14, hydrogen is 4. So that's 1 divided by 14 plus 4 plus 126.9. Let's see. 14 plus 4 plus 126.9. 1 divided by answer. That gives us 6.9. 6.9 in 10 to the power minus 3 moles of ammonium iodide. So we have our answer. D. Cambridge likes doing this. They always want you to try all of them. So personally, in trial and error sums, I do D first. But there was no way we could know that it would be the highest one, right? Okay. 4. When a small sample of hydrocarbon Q is completely combusted, it produces 3.52 grams of carbon dioxide and 1.44 grams of water. What could be the structure of hydrocarbon Q? Okay. So A is benzene. 1, 2, 3, 4, 5, 6, C6. And what about hydrogens? Basically, each carbon here is sp2 hybridized. Okay, that's why they already have 3 bonds that are used. The 4th bond goes to form hydrogen. So we have this C6H6, right? So C6H6 plus O2 gives us CO2 plus H2O. So it should be 6 over here and 3 over here. That's that. So let's see if it matches. 3.52 grams of carbon dioxide. Okay. And 1.44 grams of water. What's the AMR of carbon dioxide? It's actually 12 plus 16 plus 16, 44. What about water? It's 16 plus 2, 18. Okay, so your goal here is to find out the ratio between carbon and water. Suppose we got 6. Suppose we got 6 moles of CO2. Hypothetically, what would the mass be? Mass of carbon dioxide would be 44 times 6. 44 times 6, which is 264. What about H2O? It's 18 times 3. 54. So if you do the ratio, it should match with this 3.52 is to 1.44. So 264 by 54. Carbon dioxide to water. How much is that? 264 by 54 is 44 by 9. What about the ratio that's given? 3.52 by 144. 1.44. How much is that? 3.52 by 1.44. That gives you a value of 22 by 9. So since this ratio did not match, 1 is incorrect. 1 is not the answer. Okay. Let's move on to the next part. Let's go to this one. This is cyclo. Wait, 1, 2, 3, 4, 5, 6, 7, 8. Interesting. So the first one is benzene. C is an alkyne. D is also hexene. Hexane, but like with an alkene, it's hexene. And B is actually an alkane, but it has 8 carbons, so it's cyclooctane, right? So basically, rather than A having one bond each, it has two bonds over here. So it's actually C8. For B, it's C8H 16. All right. So cycloalkanes actually do not follow the homologous series for alkanes. They actually follow the series for alkenes. So C8H16 plus O2 gives us 8 CO2 and plus H2O. This should be 8. Interesting. Okay. Now, if you find out the mass, 8 times 44. Sorry, water should have been 18. 8 times 18. So 8 into 44, 352. 144. Okay, we got it. So 352 by 144 is actually 22 by 9, right? So it matched with the ratio we were looking for. So I'm going to go with B. There's no point in trying the other ones, right? We already have our answer. Number 5. Ethane and ethene are both hydrocarbon molecules. What is the feature of both molecules? Okay. Ethane, CH3CH3, and ethene, CH2CH2. Ethane is tetrahedral, ethene is planar. That's why A is wrong. It's not common to both. Bond angles are 109.5. Wrong. For this, it's 109.5 degrees. For this, it's 120 degrees. Wrong. It has sigma covalent bonds. That's true. Both of them have sigma covalent bonds, but pi is not correct as ethene only has pi covalent bonds, no sigma. Okay. Sorry. Ethane has both pi and sigma, but ethane only has sigma bonds. The double bond is the pi bond. Remember that, guys. 6. Elements J and L are both in group 15. J and L each form a gaseous covalent hydride in which the oxidation number is -3. In the liquefied forms, these hydrides, significant hydrogen bonding occurs only in the hydride of L. Okay, so 3 elements can form hydrogen bonds: NOF, nitrogen, oxygen, fluorine. So both of them are in group 15. So we're dealing with nitrogen and arsenic, right? AS is arsenic, as you can see here. We're dealing with nitrogen over here and arsenic. Nitrogen can form hydrogen bonds, okay? JNL each form a gaseous covalent hydride. Okay, like NH3 ammonia, where the oxidation number is 3. So we're talking about NH3. We're talking about NH3 over here. So it's -3 and this is +3, right? 3 hydrogens plus 3. Interesting. This is ammonia. In the liquefied forms of these hydrides, significant hydrogen bonding occurs only in the hydride of L. So L is clearly nitrogen. L has to be nitrogen. It can't be arsenic, okay? So L has to be nitrogen. It's between these two. Now, what about the outer shell configuration? Okay, so let's talk about the outer shell. If you're in group 15, what's your outer shell gonna be like? Basically, you have, suppose for nitrogen, it's 2s2, then 2p3. Understood? So P5 is for halogens. Please remember that. P5 is for halogens, so A is wrong. 6 has to be B. Okay? D. 7. Which gas will behave least like an ideal gas? Okay, so you behave least like an ideal gas when you have hydrogen bonding and when your number of electrons is higher. Okay, so out of these two, this is monoatomic. It's the most ideal gas. Then we have fluorine. It doesn't have hydrogen bonding, but A and D both have hydrogen bonding. So let's compare them. NH3, this has a mass of 14 plus 3, 17. What about water? It has a mass of 18, and the oxygen has 2 lone pairs. So for steam, the hydrogen bonding is more significant. So 7D is the correct answer, okay? 8. When an evacuated glass bulb of this volume, 200 cm3, is filled with a gas at 300 Kelvin and 101 kilopascals, the mass of the bulb increases by 0.68 grams. The gas obeys the ideal gas equation. Identify the gas. Okay, PV is equal to nRT. We're going to use this equation. 101 into 10 to the power 3 pascals into volume 200 into 10 to the power -6 is equal to n times 8.31 times 300 Kelvin, right? So 101 into 10 power 3 times 200 into 10 to the power -6 divided by 8.31. divided by 300. It gives us a value of n is equal to 8.1026875 into 10 to the power minus 3. Now, this is the moles. You know that moles is equal to mass by mR, right? So we can find out the AR of the gas, right? AR is equal to mass by moles. So 0.68 divided by calculator answer, 8.1 into 10 power minus 3. Do it. 0.68 divided by answer gives us a value of 83.9. 83.9. That's the answer. 83.9. So yeah, we're looking for a gas which has AR 83.9. If I look for it correctly, oh, by the way, from this year we do not have access to the data booklet anymore, but the periodic table will be provided at the end. Okay, so 83.9, that matches with krypton. Krypton is our correct answer, closest 83.8. So I'm going to go for 8b krypton. Moving on, the standard enthalpy of formation of NO2 is this, and formation of N2O4 is this. What is the standard enthalpy change for this reaction? Easy. Let's just create a Hess cycle. So we need nitrogen gas. We also need oxygen gas, but we need 2 moles of oxygen gas. So for Hess cycles with enthalpy of formation, just write down the reactants at the bottom and draw arrows upwards. Okay. Now let's follow the arrows. We either have a direct route or a detour, the direct route being the arrow on the right and the detour being the arrow on the left hand side, but our end result is the same. Okay, so for the left hand side we are creating 2 moles of NO2, so that's 33.2 times 2. On the right hand side we are creating 1 mole of N2O4, so that's plus 9.2 only, and this is del HR. Okay, so we can say that 33.2 times 2 plus del HR is equal to 9.2. Okay, so 33.2 times 2, 9.2 minus answer gives us a value of del HR is equal to minus 57.2. Interesting. So 9 should be A. Moving on. 10. Separate samples of 25 cm3 of 0.1 mole per unit cube NaOH are added to each of the different acid solutions as described. The temperature of each of these solutions was 298 Kelvin before mixing. Okay. So yeah, I heard about this question. It was apparently a tricky question. Let's try to figure this out. So separate samples of NaOH added to each of 3 different acids as described. Which statement describes the temperature rise that can occur on mixing each of these 3 acids separately with NaOH? Interesting. The rise in each mixture is the same. Uh, Basically, weaker acids do not release as much heat because some energy is lost in breaking the bond. We need to ionize it, CH3COOH. We need to break this bond. It doesn't want to break, so some energy is required to break it. So clearly, the rise won't be that high for CH3CO2H. You understand? Next one, we have, suppose this is excluded. This is excluded. Now, we want to figure out, and this is also excluded because the weaker acid can't have a greater rise. It's between B and D clearly. So we have H2SO4 reacting with NaOH. We also have HCl reacting with NaOH. So now we need to figure something out. What's the moles of NaOH? Moles of NaOH is 25 by 1000 into 0.1. How much is that? That is a 2.5. 2.5 into 10 to the power minus 3. Okay. So we have 2.5 into 10 power minus 3 moles of NaOH. Okay, but for H2SO4, the ratio will actually be 1:2. You guys need to understand that. So we're getting Na2SO4 and H2 over here. For here, this we are getting NaCl plus H2O. And to balance this out, you basically need a 2 over here. Okay, so the ratio for the one above is actually 1:2, while the one below is 1:1. Okay, what about the moles of HCl and H2SO4? It's the same, 25, basically 25 divided by 1000 into 0.05. Okay, 25 by 1000 into 0.05. You're getting a value of 1.25 into 10 to the power minus 3. Understood? For both of them, 25 by 1000 into 0.05. So we have 1.25 into 10 power minus 3 moles of this. 1.25 into 10 power minus 3 moles of this. Okay, so for HCl, basically the reaction with HCl, this one, NaOH is in excess. So extra NaOH is left. It's fine. Essentially, what reaction is occurring here? Let me use a different color. Basically, H plus OH minus is giving us H2O. And for a strong acid, this value is around minus 57. It's around minus 57 kilojoule per mole, minus 57.1 kilojoule per mole. Essentially, that is what's happening. Okay, but what about the upper one? H2SO4 is a dibasic acid or diprotic, you could say. It's a dibasic acid. So according to the ratio, we are supposed to have double the moles of NaOH if we want all the H2SO4 to react. So 1.25 into 10 power minus 3 times 2. 1.25 into 10 power minus 3 times 2 is in fact 2.5 into 10 to the power minus 3. So NaOH in fact is not in excess here. It's just enough to react with all the H2SO4. So here NaOH or the hydroxide is reacting with both the moles of H plus. As a result, we are getting this H plus plus OH minus is equal to H2O, but it's twice the value. Okay, so this is also minus 57.1 kilojoule per mole if we are talking about per mole, but in general, since we have 2 moles of acid here, obviously more moles of water will be produced and the temperature rise should be greater logically. That is why the answer is D. Understood? Moving on. It should not be the same. Okay, when would it be the same? Suppose if we had 1.25 into 10 power minus 3 moles of NaOH, then it would have been the same. Okay, tricky sum. 11. NCl3 reacts with H2O. The oxidation state of nitrogen does not change. Which statement is correct? Nitrogen remains at minus 3. Interesting. What about chlorine? So chlorine um, is plus 1 over here. Chlorine is plus 1 over here because 3 chlorines is plus 3. Oxygen is at minus 2, hydrogen is at plus 1, total is plus 2. So for here in HClO, oxygen is at minus 2, chlorine is at plus 1, hydrogen is at plus 1. So here's the thing really, hydrogen is plus 1 over here as well. This is not a redox reaction because all the oxidation numbers have remained the same. Okay, so this was a trick question. This is not a redox reaction. Which row do oxidation numbers of vanadium increase? Okay, let's see. For the first one, oxygen is always minus 2, right? So for this one, oxygen is at, for VO4 3 minus, oxygen is minus 8, so vanadium has to be plus 5 for the total to be minus 3. So here vanadium is plus 5. Then here oxygen is at minus 6, right? Vanadium is also at plus 5. Here oxygen is at minus 4, right? And since the charge is positive, vanadium is also at plus 5. So in A, the oxidation number does not change really. It's the same, okay? For B, here oxygen is minus 4. Sorry, there's only one oxygen here. So oxygen is at minus 2 and vanadium needs to be plus 4 because check this, x minus 2 is equal to plus 2, so x has a value of plus 4. Do you understand? So oxygen is minus 2, vanadium has to be plus 4 for the total to be plus 2. Next one, oxygen is minus 6, so how can we balance that? Vanadium has to be plus 3 each. 3 into 2 is 6. Next, this one we already did this. Vanadium is at plus 5. So plus 4, 3, 5. It's not working out. Okay, let's go to the next one. Here vanadium is plus 3. Here it's plus 4. Here it is. Did we found this out right over here? It's at plus 5. So this looks good. 12 looks good. 12 should be C logically. 13. A synthesis for methanol is shown. Which conditions would produce the greatest yield? It's an exothermic reaction, so we want low temperature. What about the moles of gas? Are all of these gaseous? I guess they are. So we have 2 moles of gas here and 4 moles of gas here. So we want the yield to increase or the yield to move towards the side which has lower moles of gas. So we want higher pressure, right? Then it will move to the right hand side. So I'm going to go for B. Now for 14, hydrogen and iodide can react reversibly to produce hydrogen iodide. The equation is shown. 4 moles of hydrogen gas and X moles of iodine vapor are mixed in a sealed container of volume 1 dm cube at a temperature 460 Kelvin. The system, is allowed to reach equilibrium. The equilibrium mixture contains 2 moles of hydrogen iodide. Okay. So initially we had 4 moles of hydrogen and X moles of iodine vapor. Now, in a 1 dm cube container. So since it's 1, we can just think about the moles. But if it was, something other than 1, we needed to find out the concentration. Now, the system is allowed to reach equilibrium. The equilibrium mixture contains um, 2 moles of hydrogen iodide. Okay, so initially nothing is said about hydrogen iodide, so it's 0, but at the end it's 2. The equilibrium constant for the reaction is 4. What is the value of X? This is interesting. So what's the molar ratio? 1 is to 1 is to 2, right? So since hydrogen iodide increased by 2, and it has a molar ratio of 2, remember on the product side it increases, and on the reactant side it decreases. So on the product side it increased by 2. So logically on the reactant side it must decrease by 1 according to the molar ratio. Since it's 1 is to 2, if the change is by 2 on the right hand side, the change on the left hand side should be by 1. And I told you guys on the reactant side, the moles should decrease. So we should subtract it by 1. Okay, so this should be 4 minus 1, which is 3. And this should be X minus 1. All right, this is our equilibrium moles. Now let's find it out. Let's find out the Kc. Kc here is actually Hi square divided by I2 square times hydrogen square. Okay, so Kc is 4. 4 is equal to 2 square divided by 3 square times X minus 1. All right, so let's go for it. 4 is equal to 4 by 9 into, wait, why did I use 3 square? My bad, I made a mistake over here. It shouldn't be 3 square. I wrote square by mistake, sorry. So yeah, 4 is equal to Hi square, 2 square divided by 3 times X minus 1, or 12 times X minus 1 is equal to 4. X minus 1 is equal to 4 by 12, which is 1 by 3. So 1 by 3 plus 1, that's actually 4 by 3. X is equal to 4 by 3. It should be 4 by 3 moles, which is 1.33. We should be looking for 1.33 at 14. And yeah, that's the correct answer. 14 is C. Right. 15. A large amount of N2O decomposes into nitrogen gas and oxygen gas in the presence of a tiny amount of a gold foil catalyst. The gold foil provides a solid surface on which the catalyzed reaction takes place. It acts as a heterogeneous catalyst, basically. You're going to learn about this in A2. The graph shows the concentration of N2O against time as it decomposes. The graph is a straight line. Which row describes the change in rate of reaction as N2O decomposes from 0 to 10 minutes? So basically, the change in concentration with respect to time is constant. It's a straight line. The gradient represents rate, and since it's a straight line, the change in rate is 0 because rate actually remains constant throughout the whole experiment. So this should be no change in rate. And the effect of adding more gold foil catalyst on the rate of decomposition with the same amount and concentration of N2O. So when you add more gold, since gold is acting as a catalyst, the rate should increase, right? So it would become steeper, then it might have become like this. All right, that's the logic. Very important. So if we added the catalyst, it would have become like this, gold. Nice question. Moving on to 16. The Haber process for the manufacture of ammonia is represented by the equation shown. Which statement is correct about this reaction when the temperature is increased? So remember, for a dynamic equilibrium, if you increase temperature, rate of both the forward and backward reaction increases. Okay, the answer is A, but yield would decrease. So this is a trick question and it's common. 17. NH3 is added to separate samples of NaCl, MgCl2, BaCl2 and SiCl4 under the conditions of this experiment. Only 2 samples will produce a white precipitate when NH3 is added. Okay, so this is basic in nature. Who will react with the base? Basically acids, right? So out of these 4, who is acidic really? NaCl is neutral. We say that it is not acidic. So anything with NaCl is excluded. Now we have 3 options. Okay, so SiCl4 is clearly an acid. It's acidic because when you add it to water, you get fumes of HCl. Do you understand? So SiCl4 is acidic. So it should be B because we need SiCl4 since it's acidic. Now, what about MgCl2 and BaCl2? Here's the thing. MgCl2 is slightly acidic. It forms a solution with pH, around minus 6 point, around 6.5, which is slightly acidic. But barium chloride, it is not acidic at all. Okay, it does not form an acidic solution. Aluminum chloride and magnesium chloride, these form acidic solutions. Okay, why is the ionic radius of sulfide ion greater than the potassium ion? Okay, let's look at the periodic table. Do I have it here? Can I paste it? Yeah, I still do. So what are we talking about? Potassium and sulfide. So look at potassium. Potassium is, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So for the potassium ion, this 4s1 is excluded. It has this configuration, and it has, it has 19 protons and 18 electrons. Okay, what about sulfide? The sulfide ion S2 minus. S is actually 1s2, 2s2, 2p6, 3s2, 3p4. But when it turns into S2 minus, it will turn into 3p6 basically. All right. So that's 1s2, 2s2, 2p6, 3s2, 3p6. But it has 16 protons and 18 electrons. So for potassium, it's smaller because potassium can actually, use 18 use the 19 protons to pull the 18 electrons strongly, but the sulfide ion, it has 16 protons, right? It cannot pull the 18 electrons strongly. That's why the repulsion is much greater, which is why it has a greater size, right? So the best answer over here is C, because potassium has more protons. Okay, 6 18 19 compared to 16. Which graph correctly shows electronegativity plotted against a relative atomic radius? Okay, for sodium, magnesium, aluminum, and silicon. Okay, as we go from sodium to silicon, atomic radius, atomic size actually decreases. Okay, across the period, size decreases. What about electronegativity? As you go to the right hand side, electronegativity increases. So silicon has the highest electronegativity but the smallest size logically. So silicon needs to have the highest electronegativity. I'm crossing out B and C because silicon does not have the highest electronegativity. Now, what about size? Okay, so size, I just told you that size decreases from sodium to magnesium to aluminium to silicon. Sodium should have the greatest size. So let's look for that between A and D. Sodium should have the greatest size. Okay, sodium has the greatest size. Silicon has the greatest electronegativity, followed by magnesium. Okay, magnesium, followed by aluminium, then silicon. But here D is wrong because silicon should have been over here, but it's between magnesium and aluminum. So D is wrong. A is the correct answer. Moving on to 20. The table gives information about calcium carbonate and calcium hydroxide. Which row is correct? Calcium carbonate is more soluble in water than calcium hydroxide. Never. Remember, calcium hydroxide in water forms lime water mainly. So it's wrong. Calcium carbonate is completely insoluble. You can say that it's completely insoluble. So this is no. Calcium hydroxide can be manufactured using calcium carbonate as a starting material. CaCO3. We wanna manufacture calcium hydroxide. Okay, so if you decompose it using heat, it will form CaO plus H2O. Then, you know, calcium oxide, calcium oxide plus CO2, carbon dioxide gas. Now, to form calcium hydroxide, what you can do is you can just add CaO to some water and you're gonna get CaOH2. So yes, you can manufacture it. So 20 should logically be B. It does make sense. Moving on to 21. Q is a group 2 metal and excess of QCO3, so it may be beryllium, magnesium, probably magnesium, aluminum or something. Sorry, magnesium, calcium. Typically you're not going to deal with beryllium, okay? And excess of QCO3 is added to H2SO4 followed by filtration. Okay, a sample of QSO4 is then obtained by evaporation of the filtrate. Interesting. So that means when we added H2SO4 to QCO3, we didn't get a precipitate. Why? Because it was able to pass through here and we got it as the filtrate. This QSO4 was obtained as a filtrate. If it was a precipitate, it would be stuck over here. Do you understand? So what do we understand? That QSO4 is actually soluble. It's aqueous. It's not a precipitate. As a result, it cannot be barium. Do you understand? It must not be barium because barium sulfate is a precipitate. It's between C and D. So here's the thing. For group 2 sulfates, solubility of sulfates actually decreases. So the most soluble is magnesium sulfate. So we will get it. We must get magnesium. Okay. We can't get calcium only. We must get magnesium and we will get some calcium. Calcium sulfate is sparingly soluble. So some of it we do get and some of it is stuck as the residue. 22. X, Y, and Z are three elements in group 17. X2 has, okay, group 17. We're talking about halogens. X2 has weaker covalent bonds than Y2. X2 has stronger instantaneous dipole forces between its molecules than Z2. Okay. Y2 is a stronger oxidizing agent. So, guys, we are dealing with chlorine, bromine, iodine. So, oxidizing power decreases down the group. So this is the strongest oxidizing agent and I is the weakest. Okay. And X2 has a weaker covalent bond than Y2. So as you go down the group, bond energy also becomes less, decreases. It becomes weaker. So X2 has weaker covalent bonds than Y. Okay. So X has weaker covalent bonds than Y. So if X is bromine, Y is chlorine. If X is iodine, Y might be chlorine. And if X is iodine, Y might be bromine or chlorine. Okay, that's the gist. So let's use this info. If X is bromine, X has weaker covalent bonds than chlorine. This is okay. This is fine for now. Chlorine cannot have weaker bonds than bromine. This is wrong. Iodine can have weaker bonds than bromine or chlorine. Okay, that's fine. Next. Let's go for D. Y2 is a stronger oxidizing agent than Z2. Okay. So basically, it has to be above the lower one. So for A, chlorine is a stronger oxidizing agent than iodine. This is also fine. It ticks this one. Bromine is a stronger oxidizing agent than chlorine. Wrong. Chlorine is a stronger oxidizing agent than bromine. Alright, it's between A and D. Now, last one. X2 has stronger ID forces than Z2. So ID forces depends on the number of electrons. It depends on the number of electrons. So basically, who has the highest number of electrons? Iodine. Iodine should have the strongest ID. So X2 has stronger ID than Z2. Chlorine cannot have stronger ID than iodine. But, sorry, I read it wrong. X2 has stronger and as instantaneous dipole than Z2. Bromine cannot have higher ID forces than iodine, but iodine can have higher ID forces than bromine. So the correct answer is in fact D. Okay, so 22 is D. This was a bit tricky. 23. Chlorine reacts with aqueous sodium hydroxide to form two chlorine containing products. So let's see. When chlorine reacts with NaOH in cold conditions, we get this NaCl plus NaClO, these two. And when it reacts with NaOH under hot conditions, we get NaCl plus NaClO3 plus H2O. Okay, it should be 5 over here and 6 here, 3 over here. Okay, 3 over here. Okay, all good. So what are we getting? It was 0 initially. For cold condition, it becomes -1 plus 1. For hot conditions, it becomes +1, sorry, -1 and +5. Okay, so for cold, -1 and +3. Wrong. For cold, -1 and +5. Wrong. For hot, -1 and +3. Wrong. -1 and +5. 23D looks good. Okay. 24. A catalytic converter reduces the amount of pollutants in the fumes from a car exhaust, which identifies a pollutant and shows how it is removed by the action of catalyst. Carbon dioxide. No, it is not reduced to carbon. Wrong. Monoxide is oxidized to carbon dioxide. That is true. Oxides of nitrogen is converted to nitrogen, and unburnt hydrocarbons are oxidized to carbon dioxide and water, not hydrogen. Okay, that's why D is wrong. 25. Solid R is added to a solution of ammonium nitrate, and the mixture is heated, and a gas is given off which turns red litmus paper to blue. So this is basically ammonia gas. Ammonia gas will be given off when an ammonium salt, which is acidic, is heated with a base, an alkali, something basic, right? So what is basic over here? Out of these four, what is basic? I just told you that aluminum chloride has some you know acidic characteristics. So does magnesium chloride, and p phosphorus oxide is also acidic. So the correct answer is sodium oxide. It is basic in nature. Okay, basic oxide. Next. Okay, so for 26, a skeletal formula is shown. What is the total number of stereoisomerisms, including the one shown? Okay, so basically this is a chiral carbon. This is the only chiral carbon in the compound. It's four different groups attached. This is not chiral as it has the same groups attached. So for this chiral carbon, we're getting two stereoisomers. Okay, next the double bonds. Basically, this double bond does not show cis-trans isomerism because the same groups are attached on this carbon. However, this bond shows cis-trans. This bond also shows cis-trans isomerism. The formula for cis-trans isomerism is 2 to the power n, where n is the number of double bonds. So 2 square is actually, 4. But this is how you consider it. This is how you find out the formula. The actual formula for, uh, finding out the total number of stereoisomers is actually 2 to the power n, where n refers to the number of stereogenic. N refers to the number of stereogenic carbons. Okay, N is the number of stereogenic atoms in a molecule, as well as this refers to chiral carbons as well as the double bonds. So in total we have three stereogenic atoms, or one stereogenic atom and two double bonds. So it should actually be 2 to the power 3. Okay, which gives us a value of 8. This is one way of doing it, or the other one I was teaching you. Since we have two double bonds, it's going to be 2 square, which is 4. Okay, but it's like permutation combinations basically. When you multiply these four possibilities with the two possibilities of the chiral carbon, that gives you a total of 8 possibilities. Because for this one we might have one mirror image, like we might have the lever rotatory or dextro rotatory. There are two options. If you have the dextro rotatory one, the one which rotates plane polarized light to one side, we are gonna get 4 isomers for the lever rotatory one and 4 isomers for the dextro rotatory one. As a result, we are gonna end up with 8. That's the logic. Okay, so this was a bit complicated. 26, many candidates might have got this wrong. Okay, so the correct answer is C. 26 is C. Moving on, 27. The molecular formula CH3 can represent an anion, a cation, or a free radical. Species with the molecular formula CH3 can act as an electrophile, a free radical, or a nucleophile, depending on the number of outer shell electrons. Okay, as a free radical, how? Basically, no extra protons, no extra electrons, or deficiency. Carbon has 12 protons, hydrogen has 3. So in total, it has 15 electrons. Okay, but we are only talking about the outer shell. Okay, that's interesting. So in the outer shell, if we talk about carbon, carbon is 1s2, 2s2, 2p2, and hydrogen is 1s1. Okay, so CH3 is like this. C H H H. Okay, so in the outer shell of the central atom, how many must be present? So look at this. For the free radical, for it to exist as a free radical, it needs 1, 2, 3, 4, 5, 6, 7 electrons. Okay, it needs 7 electrons as a free radical. So it's between A and D. So when does it act as an electrophile and a nucleophile? An electrophile loves electrons. It is basically positive in nature. What if we took away this electron? Then the net charge would be positive. So we need 6 electrons. And when would it be a nucleophile? If we added another electron from an outside source, it would have a negative charge. So 27 is A. Got it? 28. Compound Z has two chiral centers. A sample of Z contains all four possible optical isomers. The sample of Z reacts with hot ethanolic NaOH to produce a mixture of only three isomers. Two of these isomers are optical isomers of each other. Okay. So two stereo and one other isomer. What could be the formula of Z? Okay. Z has two chiral centers. A sample of Z contains all four possible optical isomers. Okay. So we're looking for a compound with two chiral centers. I'm going to be excluding C because this one is not chiral. It's between A, B, and D. Alright? They have two chiral carbons. Now let's look at A. When we react halogen alkane with NaOH, ethanoic NaOH, an elimination reaction occurs. So we have one option over here. When elimination occurs, it can either go to the left hand side or the right hand side. Okay. So when this elimination reaction occurs, it's gonna go to the left hand side like this. Okay. This sample of Z reacts with hot ethanoic NH to produce a mixture of only three isomers. So when we react A with hot ethanoic NH, I'm going to draw it for you guys here. This does have two chiral carbons, one over here, one over here. So one of the possibilities is this. This is the other possibility. So wait, here. What's the issue with this really? Why can't it go on this side? That's my question. Can this, is this a possibility really? Can this go on this side? The problem is this carbon over here would then have in total 1, 2, 3, 4. Is this fine? It is okay. It does not have four bonds. It's fine. This is a possibility. So either the double bond can go on the left hand side or on the right hand side. That's good. Okay, it has four bonds. So we get a mixture of three isomers. Two are optical isomers of each other. So we are looking for a chiral carbon. And yes, for A, we do have an optical isomer. I mean, we have a chiral carbon here, so we get two optical isomers there. And no cis strands. Here, no cis strands is possible either. Okay. So yeah, we are getting three compounds over here. So this is our answer. 28 should be A. What about B though? Why isn't B the answer? Because if you do break this, you can either go here, then you have a chiral carbon, you get two compounds, or you can go here. You are not restricted, so you get two compounds there as well. So in total, you're getting four compounds for B. C is excluded from the beginning. And what about D? For D, you can only form a bond here. Okay. And this is not chiral. You only get one compound over here. All right. And on the other hand, if you break this bond, you cannot form a double bond here. Why? Then this carbon would have 1, 2, 3, 4, 5 hands. That's why that carbon is that compound is not possible. Okay. So basically, you cannot form a bond here. You can only form a bond here. All right. You can only form a bond here, and that is why you get only one compound over here. This is excluded from the beginning. You get four compounds over here, and you get three compounds for A. 29. The free radical substitution reaction between methane and chlorine involves initiation, propagation, and termination. Involved in the initiation stage. Initiation stage involves this. This is basically homolytic fission of methane and chlorine. Okay, so this is what happens initially. Then the chlorine free radical reacts with CH4 to form the CH3 free radical and HCl. Afterwards, the CH3 free radical, this is basically initiation. Okay, then we're dealing with propagation. What will it do actually? It will react with chlorine to form CH3Cl plus Cl free radical. This is what happens. It's going to keep on happening. Okay. Now, this is the first step. Okay. Now, this is also propagation. Termination is basically something like this. CH3 plus Cl is equal to CH3Cl. This is termination. Propagation is 2 steps. Now, we can get another initiation reaction. How? Moving on, chloromethane can further react. It's a chain reaction. Okay. Chloromethane can further react in the next stage. How exactly? So, basically, they are telling us about the 3 steps and which row is correct here. Like, we don't need the further step. So, what is involved in the initiation stage? It is homolytic fission. And what is produced in the propagation stage? They're talking about this. Which free radical? We're getting the CH3 free radical and Cl free radical. So the answer should be B. 29 is B. Okay, that's that. 30. The alkene shows reacts with an excess of HBr via an electrophilic addition reaction. What is the major product formed? Okay, so remember, bromine will go to the carbon that has more alkyl groups because it is the product due to a more stable intermediate, which may be a tertiary carbocation or a secondary carbocation. Okay, so we have 2 double bonds here. When we break this, bromine will go to the carbon with more alkyl groups. So that is this one. We'll get bromine over here and hydrogen over here. And in this case, bromine will go here and hydrogen will go here. So what is this compound actually? If you think about it, this is actually hexane, right? So I'm going to exclude the hydrogens because we don't need them here. So this is hexane actually. 2 methyl hexane. So look at this. We have 1, 2, 3, 4, 5, 6. This is hexane. And we have a methyl group on the second carbon as well as a bromo group on the second carbon and a bromo group on the fifth carbon, right? So what is this compound? 2, 5. 2, 5 dibromo. Okay, we got 2 bromo groups on the second and fifth carbon. 2 methyl hexane. 2, 5 dibromo. 2, 5 dibromo. 2 methyl hexane. So I'm gonna go with 2, 5, right? So I'm gonna go with B. This is the correct answer. So bromine, the major product is the one where bromine goes to the carbon with more alkyl groups. That's the reasoning. Okay. 31. The diagram shows the structures of 2 halogen alkenes P and Q. Both compounds can be hydrolyzed. Which row is correct? So basically this will be hydrolyzed faster because bromine is bigger than fluorine. So the bond is longer. It's easier to break. So P will be hydrolyzed faster. And the mechanism. Basically we need to look at the compound itself. What type of halogen alkane is it? This has 1, 2, 3. 1, 2, 3. These have 3 alkyl groups. So this is a 3-degree halogen alkane. 3-degree halogen alkanes undergo SN1. Okay. So 31 should be A. 32. The structure of conine is shown. This is a common MCQ. Conine can be synthesized by reacting ammonia with a dibromo compound. Okay. Interesting. So what is compound X? Basically you need to understand how conine came to be. We reacted ammonia. Okay, so we basically had ammonia over here. It reacted with a certain compound. It reacted with this compound over here. Okay, basically like this. 1, 2, 3, 4. CH2, CH2, CH3. So basically ammonia reacts with this dibromo compound, and we have these bromo groups over here and here. Okay, so where are they located exactly, the dibromo, the bromo groups? Basically they're located, we should always start counting from the shortest end, right? So this is carbon 1, carbon 2, 3, 4, 5, 6, 7, 8. So this is basically it's basically octane, but there are two bromo groups where 1 comma 5 dibromooctane. This is our compound essentially. So what happens really, this hydrogen takes the bromine away, and this hydrogen takes the bromine away, and then we get this compound over here. So this is actually 1 comma 5 dibromooctane. So clearly, as you can see, A and B, they are wrong because they're not 1,5 dibromooctane. We need to look for 1,5 dibromooctane. Okay, so let's see what is compound C over here. They gave you Br. How does this compound even make sense exactly? They give you this Br CH2 CH2 CH2. Okay, 3 CH2s. For okay, so what is this compound? If I draw it in a better way, this is CH2 CH2 Br followed by CH2 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 CH Br CH2 CH2 CH2. This is the compound I'm looking for. Now I'm drawing C Br CH2 CH2 CH2. Then we have CH Br. Then CH2 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 CH3. In total we have 4 5 6 7 8 carbons. And where are they located? Carbon number 1 2 3 4 5 6 7 8. 1 and 4. That's why C is wrong. It has to be D. I need them to be located at 1 and 5. How exactly? Look at this one. Br CH2 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 CH2, then CHBr CH2 CH2 CH3. So this is 1 2 3 4 5 6 7 8, matches with the compound above. Okay, so yeah, this is a common MCQ, but they changed it up a bit. All right, 33. We're almost at the end. Primary alcohols can be oxidized to aldehydes using either acidified potassium dichromate or acidified potassium manganate. The reaction mixture changes color as the oxidizing agent is reduced. What are the color changes? So for potassium dichromate, it's actually orange to green. Orange to green. For manganate, it's purple to colorless. Okay, this is too easy. 33 is C. Which reaction has a product that gives a yellow PPT when treated with alkaline iodine? So iodoform test, 4 compounds give a positive result. We have ethanol, methyl ketones, and some secondary alcohols. So 2-chloropropane. No. Oh, which reaction has a product? Okay, so 2-chloropropane, CH3, CHCl, CH3. It is one with dilute sodium hydroxide, aqueous sodium hydroxide. We end up with CH3, CHOH, CH3. So this is a secondary alcohol. When you do oxidize this, if you add alkaline iodine, iodine is an oxidizing agent, you get CH3CO, CH3. So this is propanone. It does have a methyl ketone group. So 34 should be A. You're right if you're going with A. And for B, ethanol, CH3CHO, this gives a positive test, but they want us to give the product, right? If you heat it with potassium dichromate, you're going to get CH3COH, which is not going to give a positive test. Okay, that's that. 35. I'm not doing the other ones. Okay, 35. The skeletal formula of M is shown. M is reacted with an excess of LiLH4. Dilute acid is then added. Which is the molecular formula of the final organic product? Okay, excess LiLH4 reducing agent. What's gonna happen? Basically, we're gonna end up with the aldehyde and the carboxy acid, both will be reduced to form alcohols. Okay, so we have an alcohol over here, an alcohol over here, and an alcohol over here. Okay, so what's the carbon number actually? Carbon 1 2 3 4 5. 1, 2, 3, 4, 5. Dilute acid is then added. Okay, that's not going to react with anything over here though. So we have 5 carbon atoms. Then we have 3 oxygen atoms and hydrogen. If you look at it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm gonna go with D. C5H12O3. Interesting question. If you want more details, this was the compound COOH, CH2, CHOH, CH2, CHO. If you do reduce this, you're gonna get CH2OH, CH2, CHOH, CH2, CH2H. This is the compound I was working with. Okay. 36. Which compound forms a precipitate when mixed with 2,4-DNPH and also forms precipitate when mixed with phalanx? Okay, so it's a carbonyl, aldehyde or ketone, and phalanx. So it has to be an aldehyde. A is wrong, no aldehyde group present. B is the correct answer because aldehyde, which gives a positive test. This is wrong because this is an ester. This is wrong because it does react with 2,4-DNPH, but the ketone does not react with phalanx. Okay, that's why D is wrong. B is the correct answer. 37. Which reaction is a redox reaction? So it's just I can directly see it with my eyes. Ethanoic acid. Basically, remember, acid plus metal. It's a redox reaction. CH3 COOH plus Na reacts to form CH3COO minus Na plus hydrogen gas. So basically, yeah, acid plus metal is redox. Oxidation number of sodium changes from 0 to +1. What about the other ones? Ethane nitrile. Ethane nitrile. What is that exactly? Ethane nitrile? Remember, ethane nitrile is actually a 2-carbon compound, CH3CN. When it reacts with HCl, you're gonna get CH3COOH. This is basically a hydrolysis reaction, and we're gonna get ammonium. So it's not a redox reaction, by the way, because HCl already had, charge from before. Ethanoic acid with sodium hydroxide, CH3COH plus NaOH, acid plus base reaction, neutralization, CH3COO minus Na plus H2O. This already had an oxidation number. Same goes for D, alright? These are wrong. Also, electrophilic addition is redox, remember that. 38. Ethyl butanoate is a flavoring with a fruity flavor. Which row is correct? Alcohol and acid that can react to form ethyl butanoate. We need ethanol and butanoic acid. Okay. Ethanol, 2 carbon, and butanoic acid. 1, 2, 3, 4. Correct. A and B are correct. C and D are wrong. Okay, so which one is correct though? Mass of water formed when 2.32 gram of ester is formed. Okay. CH3, CH2, CH2, COH plus CH3, CH2OH is equal to CH3, CH2, CH2, COO. Let me draw this for you this way. CH2, CH3 plus water. Okay, 1 mole of water is released for each mole of this formed. So we got 2.32 grams of this. How much grams of water are we getting? Let's find out the MR of this compound. Okay, carbon 1, 2, 3, 4, 5, 6. 6 times 12. Oxygen 2. So plus 16 plus 16. How many hydrogens really? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Plus 12, 116. So 2.32 divided by 116 gives us a value of 0.02 moles of this. We are also going to get 0.02 moles of water times 18. The mass is 0.36 grams. I'm going to go with A, which is the correct answer. 39. Cyclohexene, as shown in the diagram, can form an addition polymer. Okay, let's go for it. So this was the original compound. When it forms a polymer, these hands will open up. Okay, so the hands have to be adjacent to each other. A is wrong. The hands have to be adjacent to each other. These are not adjacent to each other. B is wrong. They are adjacent to each other in C. 39 is C. Okay, they need to be adjacent to each other, side by side. Okay, 39 C. 40. 3 organic compounds are listed. Which compound will have a mass spectrum that contains a peak at 43? Okay, so let's see. This was also a tricky question that many of the candidates could not answer properly. Let's go with ethanol. We have CH3, CHO, and over here we have CH3, CH2, CH2OH, and here we have CH3, CHOH, CH3. So we're looking for 43. How? What if we break the bond here for ethanol? So ethanol in general has an MR of 12 plus 12 plus 16 plus 4, which is 44. It has an MR of 44. So yeah, we can easily get 43. How? What if we just lost, you know, what if we just lost one hydrogen? You can lose this only. You can also lose this only. So yeah, 43 is possible for ethanol. That's pretty simple. If you look at the mass spectrum of ethanol, you will get that, it is possible, really. Like, it might not be abundant, but still, a possibility is a possibility, right? You will see that on the spectrum. So yeah, if you look at the mass spectrum, you will see a peak at 43. It's very common. 44 is the M peak, but you will see one at 43. What about this? Propane 1L. 12 times 3 plus 3 plus 2 plus 2 plus 16 plus 1. The MR is 60 for both these two compounds. Okay. Now, we want 43, right? What if you break it over here? CH3 is 12 plus 3, 15. Okay, so this is 15, this is 45. That's not cutting it. What if you break it here? 15 plus 12 plus 2, 29. 60 minus 29 is 31. Okay, 31, 29. That's not cutting it either. So we're not gonna approach it this way. What about the OH group? How much does it weigh? OH group, it's actually 16 plus 1. That's 17, right? What if you actually break this? CH3, CH2, CH2, OH. You can actually break this, 17. You can get 43 over here. So this is also possible. And here you can break this. This is 17. The whole thing is 60, so this section will weigh 43. So all three are actually possible. Okay, so 40 is in fact D. That's the correct answer. All right, guys, that is all. Hopefully you enjoyed the video. It helped you a lot, hopefully. So I'm gonna link the video for May-June 2022 paper 1-1 up here, and May-June 2022 paper 1-3 down here. And I'm going to link the playlist for paper 1 up here. And remember to subscribe to the channel if you like the video. See you guys in the next one.